Hi everyone, I'm Clément and I'm going to present the work I've done with Oisin and Gabriel Brostow at University College London on unsupervised depth estimation. So we want to build a system that, given an input image like this one, will produce a dense depth map like that one, which came out of our system. In this case, brighter means closer. So why are we interested in depth? Well, depth is crucial when it comes to understanding the world around us, such as navigation and mapping. So if you are a robot, you would like to know where you are, where you want to go, how far away are things. If you want to grasp things, if you want to grasp things, and if you want to interact with the physical world around you, depth is also crucial. Finally, if you want to do non-physical interactions, such as augmented reality, let's say I want to put an object on a table right there. I want to know how big is this table, how far away is it? So how do you usually get depth? Well, I'm just going to name drop a few methods here. We have structured light, stereo cameras, or even LiDAR. So why are we interested in monocular depth estimation? Well, let's say you want to get depth for this photograph, which is a postcard from Hawaii in the 70s. Well, you can't do that because we didn't have any depth sensor at the time or any other photograph that doesn't have depth information. Well, you would like to have it. Well, we actually ran our method on this picture, and I think the result looks pretty good. Let's say you also have a physically restrictive setup, such as an endoscopy. Well, you don't have enough space to put a stereo camera or a laser scanner at the end of your endoscope. So monocular depth estimation here in this case is very useful. And finally, why not? If pirates can see the world and perceive depth with only one eye, I think we should be able to do so. So there's been some work done on depth estimation, and usually they rely on supervised depth, which means that you have a data set where you have an input color image with the associated ground truth depth image that is aligned to it. You then train a model that will output a depth, and you will rely on some loss or optimization method to update your parameters to get a better estimation. This is essentially the work of automatic photo pop-up or Make3D, which are essentially local methods relying on handcrafted features. More recently, there's been some advances, which I guess you will all figure out are using neural networks, which allow you to use more global understanding of the scene. And we have the seminal work for Hagen and colleagues, and since then, a lot of other papers doing supervised depth estimation. So you might be saying, hey, why don't we use ground truth depth and just train a model? Well, as it turns out, ground truth depth is actually really hard to capture. So to give you an idea, this is the KITTI stereo dataset from 2015. And this is the card that was used to capture data. It has two stereo cameras at the top and an expensive LiDAR scanner on the roof. This is an input image, and this is the ground truth depth that you get with it. As you can see, it is pretty sparse. It doesn't have any depth information above the horizon, and some missing objects such as this bus, are actually missing from the data because they're moving. We could also use structured light, such as the Kinect. Everyone loves the Kinect, right? However, the Kinect doesn't love the sun. It doesn't work really well outside and has a very limited range. So what do we do? Is it all doom and gloom? Well, not really. Remember, we said earlier that we could get depth from stereo. So let's say I'm capturing a scene with my stereo cameras, left and right, and I'm looking at this apple on this tree. Well, if I can solve for correspondence between these two images, I essentially get disparity, and disparity is directly related to depth. So if I can get my network from a single image to solve for disparity or correspondence, then I get depth. Let's train with stereo data. So stereo data is easy to capture. There are lots of devices around. And actually, I'm sure that a lot of you actually have a stereo camera in their pockets because the iPhone 7 Plus has two cameras on the back. So we're not the first ones to use stereo data to train models. Last year at ECCV, we had the Deep 3D model that was trained with stereo images to do image interpolation. And at the same conference, we had the work of Garg and colleagues, which also used stereo pairs to infer depth. However, they both made strong approximations in their image formation model, which led to poor reconstruction quality. And we will show you in this work that we can actually get state-of-the-art results using only stereo images at training. So how does it work? In unsupervised depth estimation, or self-supervised depth estimation, we have stereo pairs at training. Our target is one of these two images, which means that our model needs to output an image. We then have a reconstruction loss between this output image and our target image. We still want depth, however, so we need our network to output a disparity. So then how do we go from disparity to depth? Well, we just sample one of the input image using this disparity. And this is what we will call our baseline. And as our first contribution, as the sampler, we use this bilinear sampler from the spatial transformer network from 2015, which is fully differentiable, which means that we can train end-to-end and have good reconstruction quality. So to give you an idea of the results, we have an input image, and this is from the stereo KITTI dataset. And this is the result of that baseline. So as you can see, it's already pretty good. It gets the general sense of the scene. We have good boundaries. However, it has some artifacts, such as here and there. And so we didn't stop here, and we kept going, and we improved our method. And this is the result of our method. And as you can see, we solve all the artifacts. So how does it work? As I mentioned before, we have an unsupervised depth estimation. So we push one image through the network, and we sample the other one, generate another one. But then we used a commonly used trick in traditional stereo, which is to actually output two disparity maps, one for the left image, one for the right image. And then we can enforce these two disparities to actually describe the same scene, to be consistent with each other. And turns out we can also do that inside the network, which means that we can train everything end-to-end. We also, of course, output an image, and we have a loss on the reconstruction of these two images, and finally, we also have a smoothness loss on both disparities to make sure that our output is very smoothly. So a few words on the architecture. It's fully convolutional, which means that you can pick whatever encoder you want. We used VGG-like and ResNet 50. We used skip connections between the encoder and the decoder, which is similar to DispNet and FlowNet, which are from Thomas Brox's group. We also have a multi-scale generation, which means that we generate the output at multiple scales, and we also have a loss at multiple scale. And finally, it is fast. The current model, which wasn't optimized for speed, actually runs at 30 frames per second on a Titan X. So now let's see a video of the result. This is a video of the test on KITTI. The network has never seen any of these frames, and every single frame is processed independently. There is no information on video or temporal information. All the frames are independent from each other. As you can see, we reconstruct all the pedestrians, the walls, the signs, and the road. So now let's compare with other methods. So this is an input image from KITTI, and this is the ground truth depth, which we interpolated for visualization purposes. As you can see, the top part is missing. And I will go through the results of other methods. So we have Eigen, Leo, Garg, which is our closest competitor, which is also unsupervised and from ECCV last year. And this is our result. As you can see, we resolve more details and we're more faithful to the input image. We also ran some numbers. We had a thorough and careful evaluation. We rerun most of the other methods, and we compare with the same evaluation code, which we share with everyone. And as you can see, we beat all previous supervised methods, as well as unsupervised methods. So that means that with stereo pairs at training, we can actually have state-of-the-art results versus methods that actually use ground truth depth. We also run our method on unseen datasets, such as the Make3D. So this is an input image. This is the ground truth depth. Karsh, Liu, Lina, who is state-of-the-art on this data set, and our result. As you can see, we are pretty good around the edges of the scene. So there are a few things to know about our method. Because we're based on a reprojection loss, it means that everything that is not Lambertian will have unreliable depths. So this could be solved with more supervision, which actually was studied by a paper which was presented 2 days ago, subsequent work. We also need calibrated data, which means that it needs to be synchronized and rectified. However, if that's too much for you, then you should stay for the next talk where they used less supervision at the expense of reconstruction quality. So as a conclusion, we can get depth from a single photograph. We get self-supervision from stereo data, which is both cheap and scalable. Our method is accurate as it beats all previous results on KITTI dataset. So we made the code and the models and the evaluation code available for everyone. You can just search for monodepth. If you have more questions, come at the poster 21. And this is a video I took yesterday in Hawaii. And as you can see, it does a pretty good job, actually. Thank you.
Okay, so we have time for questions. So again, there are a number of microphones here in the room. Best is to use that. Otherwise, you can also try to tweet and maybe we'll find the questions. To get started, maybe I have a question. So with stereo, there are ambiguities, in particular if you have horizontal lines aligned with the epipolar lines. So those will tend to systematically be, essentially be missing in the left-right ray projection will essentially always, fail there or most of the time, meaning that you systematically miss that in your training data. Did you address that? Did you think of how you could solve that? Did you consider tween-ocular setups that could actually help with that?
So it's a good question. We didn't really have that problem because most of the issues usually are with vertical objects in terms of loss, and it was doing a pretty good job with that. But you could surely use more than 2 cameras or like space them differently in space. But we haven't tried with this method, but it could definitely be done.
Okay.
So you said that it makes a Lambertian world assumption. How much, you use the KITTI data set where there's a lot of specular things. Do you have any kind of qualitative intuition on how much highly specular surfaces affect output quality?
It's a good question. Actually, if you look at the results, you can see that the car hoods are usually slightly bumped in, as well as the windows. And the KITTI dataset used CAD models, so the windows are actually at depth of the window. So we probably have a bit of loss there, but we actually don't have a quantitative evaluation of that. But it didn't seem to hurt too much.
Okay, thank you.